Okay, welcome back. It's time for the last talk of our kickoff meeting, cherry on the cake, current trends in non-commutative geometry. David Kyed from Syddansk Universitet, Denmark. It's all yours. Take it away.
Thank you, and well done with the Danish pronunciation.
I did my best.
I'm going to present the last work package, and I have decided, since it's rather late, at least on this side of the pond, to try to make my talk relatively short and as non-technical as possible. So it has to do with a certain corner of the non-commutative landscape that you all know quite well. We start with the C-star algebra, and then we impose all sorts of axioms on it, trying to mimic various things that we see in the theory of classical spaces. And one thing that one can ask, and this is what Riefel did back in the 90s, was how does one model suitably not the existence of a topology, but the existence of a metric, metrizing the topology, of course. And after quite a bit of thinking, he came up with a theory of what is nowadays called quantum metric spaces. And these are intimately linked with Kahn's non-commutative geometry, and this is the corner of this non-commutative landscape that I would like to zoom in on. And I think, without any further ado, I'll just give you the definition, or one version of the definition. So it'll come as no surprise to any of you that you start out with the C-star algebra, and as soon as you see the adjective compact, you will also not be surprised to see that the C-star algebra is supposed to be unital. But now the more subtle thing is, how do you model the existence of a metric on the non-existing underlying topological space? And Riefel's suggestion is that you model that using a semi-norm defined on your C-star algebra, and it's allowed to take the value infinity, but except for that, it's supposed to be an honest-to-God semi-norm, and it's also supposed to be invariant under the star operation. And these are very mild requirements, but now here come the main axioms in increasing order of importance. So the first and maybe least severe axiom is that the semi-norm is supposed to vanish on the unit of the C-star algebra in question. So you see right away that it's something which is quite different from the ordinary C-star norm, which takes the value 1 at the unit. And I'll give you an example in a few lines that will tell you why this is reasonable. The second axiom is saying that this being infinite business is not getting too much out of hand, namely that if you look at the part of the C-star algebra upon which the semi-norm is actually finite, this constitutes a dense and automatically star invariant subspace in the C-star algebra. And then the real axiom is that if you look at this metric that you can define on the state space of the C-star algebra, and you define it by looking at all the different values that your two states can take when you let your input vary over the semi-norm unit ball, this is supposed to metrize the weak star topology on the state space. So a priori, there's nothing preventing this DL from being infinite. It could happen. So part of the requirement is that it's finite and hence a genuine metric. And this genuine metric is then supposed to metrize the weak star topology on the state space. And this is the data that defines the compact quantum metric space, so the pair A, L satisfying these requirements. And when all these things are satisfied, the L is then called a Lip norm. And I think I owe you the canonical commutative example right away, namely if you start out with a genuine compact metric space, then you really ought to be able to build one of these compact quantum metric spaces out of it, and this is indeed the case. You just pass to the the commutative C-star algebra of continuous functions. And then your Lipschitz norm, or your Lip norm, is just associating to a function the smallest Lipschitz constant available for this function, which could quite easily be infinite, but it is a well-known fact that the Lipschitz continuous functions are indeed dense in the continuous functions. So the second action up there in the definition is not a problem. It is also easy to see that if you plug in a constant function, for instance, the constant function 1, then it'll clearly have Lipschitz constant 0. So the first axiom is also not an issue. But the last bit about metrizing the V-star topology is actually not completely trivial. But since this is very classical stuff, you can actually find it in some old papers from the 50s by Kantorovich and Rubinstein. So this is all very well known. But we are, of course, in our line of business, much more interested in non-commutative examples. So let me give you a couple of examples showing where you can find these quantum metric spaces in our neck of the woods, so to say.
Sorry, David,
So,
it's completely obvious that now if I use this LD Lip norm as defined here at the very bottom line, and then I use the definition of the metric given by this Lip norm in point 3 of the definition, but I'll get back the metric I started from.
It is not completely obvious, but it is true. So if you view your space X as embedded into the state space as point evaluations,
yes,
you get exactly that this metric DL restricts to the original metric. So there's a full recovery of the metric structure here. So I wanted to show you a couple of examples, and the first part of these examples come from group actions. So imagine that you have a compact group acting on a unital C-star algebra in a ergodic fashion. So only the scalars are fixed. And let's assume, for instance, that this group G is endowed with a metric metrizing its compact topology. Then out of this dynamical structure, you can define one of these Lip norms. And this goes back to one of Riefel's foundational papers from the 90s. You just take all these difference quotients, so to say, of your action of the compact group and take the soup of what you get. And this defines a compact quantum metric structure on the C-star algebra A, which is then sort of induced from the action of the group G. And what could you do? Well, one thing you could do is you could look at something like SU2, for instance, with its standard Riemannian metric. And SU2 has an n+1 dimensional irreducible representation for every n, and you can just let it act on the corresponding matrix algebra by conjugation. So in this way, your matrices become compact monometric spaces for this natural action of SU2. Another and more infinite dimensional thing you could do is you could look at the non-commutative torus, and then you could start...
Wait, sorry, David, wait. Is it obvious that this action is ergodic?
Maybe not, but it is true.
Okay.
What did I want to say? Well, yeah, you could take your non-commutative torus. It's sort of defined by these two unitary operators, and you can start rescaling them by elements from the unit circle, and this will give you an action, and this will give a compact quantometric structure for the non-commutative torus as well.
Okay.
So these are things that you can do. And another source of examples comes from sort of ordinary non-commutative geometry. So if you take a spectral triple, I'll trust that you still remember Brahms' definition of a spectral triple, so I'll not go into the details about that. And we don't need anything fancy like compact resolvent here. The only part of the spectral triple that we need, for now at least, is the fact that the algebra A has bounded commutators with the Dirac operator. And this means that you can take the operator norm of this commutator, and this will give you a number. And this way you get a semi-norm. And you might expect me to say now that this always gives you a compact quantum metric space, but it's not so, right? So even if you take a fully fledged spectral triple, you may or may not get a compact quantum metric structure. And it is one of the open questions that would be nice to get a handle on. When does one get a compact quantum metric structure? How do you detect this from the spectral data of the spectral triple? And yeah, this is I think wide open. I'll give you some examples where this is the case, but one reason why this could fail is that the Dirac operator could simply just commute with more than just the identity. You can cook up examples where this is the case, and you can show that if you do have a quantum metric structure, then actually the only kernel of the semi-norm is the scalar multiples of the unit. Anyway, so what is good about this theory? One, and I think the main sort of claim to fame, is that the classical form of Hausdorff distance has a very nice generalization. And since I wanted to keep my talk fairly short and as non-technical as possible, this is where I will gloss over most of the gory details. And if any of you feel that I should flesh out some of these details, I'll happily do it. But just
David, can I ask you, can you come back one moment to the previous example?
Yeah.
Page. So can the last example be viewed as corresponding to group action of the unitary group generated by D on the algebra? So
that it fits with the first?
Yes.
I think not, because there are also examples where, so I gave you one obvious reason why this could fail, but there are also...
Yeah, but then also this would be not ergodic probably if there is commutator more than
right.
Than one. Okay.
But you can remedy that. I mean, you can find examples of spectral triples where the commutator does only, or the Dirac operator only commutes with scalar multiples of the identity, but where this LD still fails.
Okay.
So there is a difference between the two settings.
Okay.
So but maybe what you're pointing to is a good question, namely, what is the link between the structure in example class number 1 and example class number 2? And I use the term example class loosely in the second case because it's not always, examples.
Thanks.
Yeah, you're welcome.
Since we're on this slide, I have a slight problem with this V. I mean, I don't see how circle can act ergodically on the quantum torus.
So
why is it ergodic action?
I didn't check. I think it should be, but maybe I'm wrong.
Unless, okay. Like in the, but that's not, sorry. When you have Kronecker foliation, of course, I can act by R on the visual torus, and this would be ergodic action of R on the two torus, which of course is not proper. But here I'm really having problems in S1 is compact. So whatever action you cook up, I don't see how it can shrink the quantum torus to a point. There is an obvious two torus ergodic action on the quantum torus. That's obvious. But I don't see how you can do it with just one circle, not the Cartesian product of two circles.
Branimir is raising his hand as well. Is this attached to Piotr's question or?
It's to Piotr's question. I mean, it's yeah. I mean, the U1 invariance, like, I guess you can have a diagonal U1 action on scaling the two generators the same way. That's going to have non-trivial fixed points of algebra.
Exactly, yes.
Yeah.
But the two torus act perfectly well, and indeed there's this old characterization due to Olus and Pedersen and Takasaki, I guess, that if you have a compact abelian group acting ergodically on a C-star algebra, it's basically just they're literally just the theta deformations. Let's
soup up from S1 to the two torus.
Then I'm completely happy.
Okay, if everybody's happy with the two torus acting instead of the circle, then and I'll correct the slides so that it fits again. Thank you so much.
It's even free then.
Yeah.
Yes, so it's a Galois object, yes.
Very good. I'll make sure to fix this. Any other issues with this slide number 4 before I continue? All right. So I wanted to tell you about this quantum Gromov-Hausdorff distance, and I don't want to get too far into the technicalities, but I wanted to remind you roughly the idea in the classical case. So if you have two metric spaces, M1 and M2, if you want to measure their Gromov-Hausdorff distance, you just look at all possible ways that you can stick M1 and M2 into a common metric space and see how well you can make them align. And then the smallest, the best possible way that you can do that will be the Gromov-Hausdorff distance between the two metric spaces M1 and M2. Now, you can imagine that sort of isometric embeddings can be dualized to the C-star algebra level, and this way you get a natural candidate for what could be called a quantum Gromov-Hausdorff distance between compact quantometric spaces. And Riefel worked this out back in 2004, and there's quite a bit of work involved in it, but when the dust settles, you will have a symmetric distance function which satisfies the triangle inequality, and this is all fine and good, but it does have a certain drawback, namely that distance 0 does not mean what you might expect it to mean. Namely, as a non-commutative topologist, you would say this should be a lib-norm preserving star isomorphism, but it's not. It can be formulated in terms of a lib-norm preserving isomorphism, but not of C-star algebras, but of the underlying order unit spaces of self-adjoint elements. For the lawyers, I am lying ever so slightly here, but it is a matter of technicalities. This is sort of the main moral of the story.
Do you mind reminding us what order unit spaces are?
So I will do the cheekiest thing and say that they are subsets of the self-adjoint elements of unital C-star algebras. So with the order structure coming from the self-adjoint elements and containing the unit. So I just pass from my C-star algebra to its associated ordered space of self-adjoint elements.
Okay.
Yep.
Okay.
But so this is just part of the story, that this is how it goes, but there are ways to fix this. So one way, and presumably the most relevant way these days, is Latremollier's different versions of his quantum propinquity. So this is an elaborate version of Riefel's Gromov-Hausdorff distance, which takes into account more structure. And it is indeed so that if you have order distance 0 there, then really you do get a star isomorphism intertwining the two lib norms. And there are other ways of doing it. There's a matricial version of this quantum Gromov-Hausdorff distance, which is due to David Kerr and Hanfeng Li in two different papers, and then a third paper that shows that the two different constructions are actually the same.
David, since it's already late into the day, we need some distractions to keep us going. And I couldn't resist checking, we already have obviosity, we have propinquity, so many beautiful words. And I just found in the Wikipedia of what propinquity means, and it's wonderful. In social psychology, propinquity it means that it's one of the main factors leading to interpersonal attraction.
Oh,
So that sounds really cool. I mean, so we have spaces who are interpersonally attracted to each other. That's,
I can't take any credit for that. It's all due to Frederic. But it does sound poetic.
Yeah, very French, very French.
Yeah.
Okay.
So once you have such a quantum distance available, you can sort of start treating all of these objects from a much more analytical point of view. You can ask whether two quantum metric spaces are closed. You can ask whether a sequence converges to another quantum metric space. And this game has, of course, been played for about 20 years now, and a ton of positive results are available. I'm just going to drop now a list of things that you can do. I will not go through them in detail, because I just want to sort of convey the idea that various natural classes of examples have been treated. For instance, maybe one thing to single out is the first point here, namely that the fuzzy spheres, which is sort of physics lingo for matrix algebras, they converge to the classical two-sphere. And this is Riefel's original result back from 2004.
And look, David, this actually answers a question I wanted to ask you later on, but now that's an answer. You see, if you have a limit of graph-sister algebras, in the limit, in this sense of convergence of Riefel, it need not be a graph-sister algebra again. This is exactly what you have here. Matrix algebras are, of course, graph-sister algebras, and you take their limit in the sense of Riefel, they converge to two-sphere, which cannot be. It's not.
Yeah.
Okay.
Yeah. So, I mean, what is left to do, you might ask? And one thing that is left to do is the thing that you're pointing to right now. I hadn't really thought of like phrasing it as a concrete problem, but what kind of structure is preserved under this kind of convergence? What kind of structure is preserved from being close? Like, imagine that you have two of these quantum metric spaces that are like 1/10 billion apart from each other. What does this, can you transfer any sort of structure? And as you can see, clearly commutativity is one of these things that's not transferable, since you have matrix algebras converging to the sphere.
Exactly.
So I'd like to sort of zoom in on three sort of overarching research directions that are trending right now, I'd say. And one of the things that is really going on in many different research groups is this connection between differential non-commutative geometry and metric non-commutative geometry. So more precisely, getting a better connection between quantum metric spaces and spectral triples. And on the propinquity side of things, Latremoullière and his co-authors have been working on this thing they call spectral propinquity, which is something that you can apply to those spectral triples for which the Kohn semi-norm gives rise to a compact quantum metric structure. And this is exactly designed in such a way that if you have spectral propinquity 0, then you have a unitary equivalence between the spectral triples in question. So in particular, the underlying C-star algebras are isomorphic in a very strong way that is sort of also transporting all of the geometric data. And this is, I think, not at all fully explored, but let me highlight one thing that does come from this. If you have a bunch of spectral triples that converge in this spectral propinquity, you do get that somehow the spectrum of the limit is the pointwise spectrum in a certain sense of the pointwise limit of the spectra of the constituents of the sequence. So there's a certain amount of spectral information that is carried over in the limit.
Mm.
So I think there is a lot of work to be done in this direction. So I wanted to advertise that aspect of the theory. And also there is a certain tendency that some of the classical results are also being turned into a more geometric flavor. The fuzzy sphere result by Riefel that I mentioned on the previous slide has been upgraded to sort of a more geometric direction recently. And also quite recently, last December, I think, the solenoid theory has also undergone the same development. So I think this is sort of one overarching research theme that fits under this work package.
Mm-hmm.
Another thing is one of my personal hobby horses, namely Q deformations. And here I mean in the Warsaw school of the word. So you quantize by turning to a unital C-star algebra, and the most important example here is Voronovich's quantum SU2, which I will get to in a second. But I would like to start with the Potash sphere, the quantized 2-sphere, because this fits on the nose into a spectral triple. This was done by Dabrowski and Sitash almost 20 years ago by now. And this spectral triple does indeed give you a compact quantum metric structure. This is a more recent result by Konrad Aguilar and Jens Kuhl. So you now are in the framework where you can start asking all sorts of continuity questions. For instance, what happens when you start moving your deformation parameter Q around? And if you work a bit, you will see that this actually forms a continuous family for this quantum form of Hausdorff distance. So in particular, these non-commutative quantum spheres will converge to the 2-sphere with its round ordinary metric as Q tends to 1. And so this is one thing that came out of our work recently. And you can even deal with SUQ2 itself, because even though you might not be able to give it a good spectral triple, there are tons of Dirac operators around. Some of them give rise to spectral triples, but they all seem to have various problems associated with them. But if we do not necessarily care too much about whether we get a spectral triple, if we take these Dirac operators, a suitable family of them indexed by say Q, and as the discussion before indicated, there is actually an additional parameter T that I'm also completely ignoring now, because I just want a 1-parameter family for this presentation. You can get compact quantum metric structures on SUQ2, and not too surprisingly, but requiring quite a bit of work, you will get that the SUQ2s will converge to the classical SU2 with its round 3-sphere metric, well, adjusted by a factor of 2, but essentially the round metric.
But this is very interesting, both SUQ2 and S2Q, because their C-star algebras do not depend on Q. So
No.
if you look at it as topological spaces, that's basically a constant sequence, okay? So it shows that here in this formalism of CQMS, this Q plays a crucial role. It really changes your metric structure.
Yeah.
With a topological phase transition at the end of the day, because even topologically speaking, SU2 and SUQ2 are of course different. One is quantum, one is not.
Absolutely. So what you the key to these convergence results is actually to zoom in on a commutative sub-C-star algebra. So if you take in the classical Voronovich lingo, I think it's called gamma. So you do gamma star gamma.
Yes.
Then you get its spectrum is sort of a quantized interval.
Exactly, yes.
And you can compute completely explicitly the induced metric there. And there you can really see how it shifts around with the Q. And this explicit formula for the metric on this quantized interval is really the key to these two convergence results. So, yeah. And what is left to do here? Well, a lot of stuff is left to do. These are just the two most natural candidates around. And right now, Jens and our PhD student, Max Mikkelsen, are working on the complex projective plane and the quantum five sphere.
David, sorry, let me interrupt you one more time on the funny note. For us, it's very confusing because we got used to Emma Sophie Mikkelsen, who recently changed her surname, and now we see Mikkelsen and we think about Sophie, but no, it's Max.
No, yes, and there's no relationship between them except for the surname. Or in her case, previous surname. So Max Mikkelsen is writing his PhD right now with Jens as his main supervisor in Odense.
Yeah.
So, and you notice here that there is a graph algebra connection, right? Because these are indeed graph C-star algebras, and there's a whole avenue that you can go down here and try and explore to what extent does this quantum metric business work at the graph C-star algebra level. And I think it's completely unexplored territory. So if you're looking for a good research project, just look around and see what you can find. All right. I have a feeling that time is sort of running a little bit short already.
No, so but it's perfect. We have 13 minutes. So
13. Okay. Excellent. So let me just here at the end zoom in on another bunch of issues that are appearing in this line of business, and the setting is that of a good old-fashioned discrete group gamma. And let's assume that we have a length function on it. So for instance, my gamma could be finitely generated, and then the length function is just measuring the number of letters that I need to use in order to express a certain group element in the generators. And then you can define an unbounded operator on the L2 space of gamma, and you just take the natural orthonormal basis, and then you rescale the gamma basis element by the length of gamma. And this, unless this length function is very silly, this will be an unbounded operator, and it'll be have a self-adjoint closure. So you can give you can ask whether the con semi-norm turns the say reduced group C-star algebra into a compact quantum metric space, and this turns out to be quite difficult actually. It may look innocent, but it's very difficult. So first and foremost, there are no counterexamples known. So for all we know, this could be the case always. So there are some positive results, and they are relatively few. So the sort of basic two classes of examples for which this is known is for the class of hyperbolic groups and for the class of nilpotent groups. Both of these classes are sort of extended a little bit, but for the sort of sake of trying to convey the main ideas, these are the two classes to keep in mind. So there is certainly also a lot more work to be done in order to clarify this, and I'm trying to get into this line of business in the spring. So I don't really know where the results are going, because it's too premature to say, but clearly one of the things that one would expect is that the class of hyperbolic groups and the class of nilpotent groups they have one feature in common, namely being of rapid decay. So one thing that could conjecturally be the case is that if you have a rapid decay group, then this Dirac operator DL should give rise to a compact quantometric space, but I don't know. So I think these are the problems that I wanted to mention, but in case anybody is interested in joining us in these quantometric space problems, I have included a very non-exhaustive list of references, but it's a relevant list in that most of the papers contain a bunch of references, and if you go through the references in the references, you should be fairly well covered. And if you get lost in the literature, you are very welcome to just get in touch, and I'll try to see if I can navigate it with you. All right, so that was all I wanted to say.
Thank you very much, David. Now we still have 9 minutes for a discussion. So who would like to begin? Any of you? No? Tomek, you haven't spoken today yet. Give it a try.
I cannot imagine a question now.
No. Okay, Branimir.
Yeah, with regard to the group stuff, there's I mean, maybe it's just some spaghetti thrown at the wall, but I mean, there's a certain school of thought according to which one should think of a positive definite length function as something akin to the symbol of the Laplacian, which means that the more natural candidate for the symbol of the Dirac operator would be, like in the case of the aura property, a proper one-cocycle. Or an isometric action. So I was wondering if, and this actually, when you think about Zn as the Pontryagin dual of the n-torus, this works out perfectly. Your one cocycle is your inclusion in Rn. So I was wondering if there was anything in the direction of proper one cocycles.
I don't know. But you're right that in some sense the DL is sort of the square of what you would imagine a Dirac operator to be. It's positive, right? And so it'll give a trivial class in K homology, for instance. But the short answer is I don't know.
Okay, anybody else? I don't see any volunteers. So let me ask some really cheap questions, if you don't mind. So for instance, I would like to see what is the Gromov-Hausdorff distance between, I don't know, a two torus and a two sphere. And then you go to propinquity, and what would be this propinquity between, I don't know, 3x3 matrices and 2x2 matrices? If you can define distance between metric spaces, well, I would expect some numbers. They are definitely non-zero, right? They are definitely positive. So what are they? And of course, here it's obvious that I would like to see that somehow the distance grows with the genus. Okay, I'm further and farther away from a sphere, from the two sphere. When I compute the Gromov-Hausdorff distance, the bigger genus I have in my, say, compact Riemann surface. And say with matrices, you know, the bigger the dimension is, the further away I become from, I don't know, 2x2 matrices. So any,
I don't know of sort of concrete computations like that. They might exist. In general, it's not super easy.
Yeah, I would imagine. I mean,
exactly right. You can get upper bounds, but sometimes you can get lower bounds as well. But getting the concrete number out is not necessarily that easy. Even with matrices, I don't know if there are concrete computations. So that is also something to try and do. What do you actually get?
But maybe this matrix example is of opposite nature. If you think about a fuzzy sphere.
Yes.
Okay.
Yes.
Then there could be some effect of accumulation. So the distances between big matrices could be small.
They would get small. Yeah, they will
Yes.
certainly get small because they have a limit point, so they will
Yeah, yeah.
form
Exactly,
a
Cauchy sequence, yes.
But the distance to 2x2 matrices as n
Oh
goes
yes,
to
of course.
yeah, that I don't know.
Jack, go ahead. What's your question?
Thank you. Let me see if I can actually operate my computer.
Well, with the operator algebra that one can see, so it should operate it in a way that we can see you.
Yeah, well, so sometimes the operations work. You know, can you hear me?
Yes, yes.
We hear and
So,
see you.
You cannot see me?
We
We hear you and we see you, yes.
Okay. Well, this is a miracle, isn't it? So there was a point early in your talk. You were talking about the lip norms coming from spectral triples, and you mentioned that not all the axioms of spectral triple are really necessary to get the lip norm. I wonder if you could expand on that a bit. What I think you said that the you don't need the compact resolvent for the Dirac operator necessarily.
I wanted to say that I don't need it in order to define the semi-norm. And all I need is for the smooth algebra to have bounded commutators with the Dirac operator, because then I can take the commutator norm and have a semi-norm.
Okay.
But whether the semi-norm gives you a quantometric structure is, as you could see also from the discrete group case already, a very subtle issue.
Yeah, so it almost would seem that if the when the operator doesn't have compact resolvent, it's even harder for the unit lip ball to metrize the state space topology.
Yeah, but you can have this in the case of the Pottish sphere. The commutator in the case of SUQ2, then these Dirac operators that exist on quantum SU2, they don't have bounded commutators, but they have bounded twisted commutators. Okay, so you just take this twisted commutator instead of your ordinary commutator, and then you take the operator norm. And then you do get a quantometric structure, but they do not have compact resolvent. So it's very foggy for me at the moment. What's the interplay between these different conditions here? And I would really love to see it somehow dissected a little bit.
Well, thank you.
Yeah, you're welcome.
Okay, great. Anybody else? So maybe just to finish, let me ask the following sort of wishful thinking question. You presented this nice result, a positive result for hyperbolic and important groups. So we have this recipe, we have a discrete group, and we have Dirac coming from the length function, and then we have a criteria, some sufficient criteria for discrete groups to ensure that we get compact quantum metric spaces, okay? And now imagine that instead of a length function, you take, say, graph-sister algebra, and say you take the paper of Aidan Sims and David Pask from many, many years ago, and I presume they also have some recipe that says, all right, give me a graph, I'll give you a spectral triple. And I was wondering if we can have now some conditions on graphs that will guarantee that for this spectral triple will yield necessarily compact quantum metric space. Would it be a natural question to investigate?
Absolutely. I think that understanding graph-sister algebras from the compact quantum metric point of view is interesting and wide open. So I just don't know of any results in that direction. So if anybody feels up for it, with a little bit of luck, there are some low-hanging fruits around. But I don't know. I'm not going to make any bombastic statements in that direction.
Of course, but we are supposed to indicate some first research steps that can be taken, and it occurred to me that it might be one of such first research steps, because you have some concrete things to do, and then you just try it.
Absolutely. Yeah.
Okay, guys, this is perfect timing. Thank you so much, David. Thank you all. I stop the recording. I finish our kickoff meeting, so let me stop the recording first.